notification.
1 minute. Okay. Okay. Fine. Fine. Fine.
We are live. Hello, sir. Can you hear me?
Yeah, we can hear you, but little louder actually.
Okay. Does this make it better?
Yeah, slightly better. Yeah.
Okay, I'll start. Hello, folks. Today we have Professor Ryo Ohmura joining us. Hello, folks. Hello, folks. Today we have Professor Ryo Ohmura joining us. Professor Ryo Ohmura is a professor in the Department of Mechanical Engineering at Keio University. Professor Ohmura and his research group have contributed significantly on understanding and solving environmental problems and developing new efficient energy utilization technologies. He's a recognized expert in the field of gas hydrates and has published close to 200 papers. His research team has recently developed a world's first technology to stably store ozone and continuously generate ozone hydrate. Thank you for being here, Professor Ohmura. I give the stage to you.
Okay, let me start my presentation by sharing my PowerPoint. Okay. And, okay. So can you see my presentation? It is
Yes,
working.
Professor. Yes, it's perfect.
Okay. So my name is Ryo Ohmura, and I'm a professor of department mechanics. I'm a mechanical engineer, but working on the cross-rate hydrates. Today, I would like to talk about some cross-rate hydrates fundamentals, physical chemistry, and applied technology towards the carbon neutral age. Okay, let me start. So, so before going into the substantive parts, I would like to briefly mention about my university. So the Keio University, this is, I think, honestly, this is not very known worldwide. So we are not necessarily very strong in terms of the world's university ranking, but actually in Japan, this is the oldest. We have a longest history as a modern school. This Keio University established in 1858. We have over 160 years of our school history. So, and this is, I can say that this Keio University is the best private university in Japan. So this is our characteristics. We are a private university. Different from the University of Tokyo, Kyoto University, or Tohoku University. In Japan, we have several such famous research universities, but they are all national university governed by the national government. But we are independent. We are in the private sector. This is some interesting aspect of our school. So, and then I would like to talk about briefly again at the science metrics myself. So my H index, the score is defined on the Web of Science is now currently 37. And my total number of the publications, again, indexed in the Web of Science is 188. This is 4 times greater than my age. So very recently, I achieved this number. Okay, so then I move on to some research aspects of my group. So I totally working on experimentally on the compound called cross-rate hydrates. And my expertise is both on the fundamental aspects and also applied aspects. So I do the fundamental physical chemistry, so as well as applied technologies related to the energy and environmental issues. So for example, as a fundamental physical chemistry, so I measure, for example, phase equilibrium of the cross-rate hydroforming system and prepare the crystal sample for the solid phase characterization. And so for the X-ray diffraction characterization, that is helped with my collaborator, Dr. Takeya in ASD in Japan. Also, I work with some Canadian researcher, Dr. Saman Arabi, to do molecular dynamic simulation to understand the molecular level understanding of this compound glycerol hydrate. Also, I even work with some quantum chemistry computation. So together with he is the applied physicist, Dr. Rodion Beresrudov in Tohoku University. So I do such a very fundamental physical chemistry, but this is the foundation for the application of the glycerol hydrates. So with glycerol hydrates, we can do the energy storage, like a thermal energy storage, or even hydrogen storage, or we can do some applied thermal engineering, heat pump engine application. Also, we can do the carbon capture, gas separation, and also ozone storage technologies. So this is some rough explanation of my research group expertise. Okay, so then I would like to briefly speak about the definition of the glycerol hydrates. So this is a solid, and this is a crystal that physical compound composed of the water molecules that is hydrogen bonded to form the cages like this cartoon. Now within this hydral water cages, there is some molecules that is different from the water. This is called gas molecules. So the example of the gas molecule can be the methane, carbon dioxide, nitrogen, oxygen. So a lot of molecular compounds can be the gas molecules. I think that hundreds of the compounds, molecular compounds, or some partially ionic compounds are known as the gas currently. So you can see that some crystallographic structure of the hydrates. So depending on the chemical species of the gas, so the crystallographic structure of this compound glycerol hydrate slightly changes, like a structure 1, structure 2, structure H. These are the 3 well-known crystallographic structure. You can see this cartoon. So this is from the snapshots of the molecular dynamic simulation. There is in the blue parts. This indicates the hydrogen bonds between the water and water. So that it's forming the cages. And you can see that yellow spheres that enclosed in the cages. This is a molecular level crystallography of the hydrates. Okay, so I would like to show some the video that is from the created from the molecular dynamic simulation. So there is a water molecule here. So you can see the oxygen with a red sphere, and this gray sphere is the hydrogen. So so hydrogen is connected to the neighboring oxygen through the hydrogen bonds. So with these hydrogen bonds, the water molecules forming the cages. Of course, at the molecular level, they have some vibrations. And within this molecular level cages, you can see that here, moving different molecules. This is, in this case, this molecule is a difluoromethane. There is the carbon in the center here, but there is 2 hydrogen and 2 fluorine. So this is a crystallography of this compound. Okay, so if we go scale up of this visualization of the hydrate, you can see there's some microscope scale pictures here. So this is a methane hydrate. This picture shows the methane hydrate. You can see that some dendrites, dendritic crystals is growing in the liquid water phase that is saturated with water. This is methane hydrate. So this is some similar picture that is here, but this is carbon dioxide hydrate. Growing in the carbon dioxide saturated liquid water. So this is a microscope scale observation of the hydrates. So, and then we may go much more macroscopic view of this compound. You can see that there is an reactor. This is actually a high pressure reactor, but opened after the hydroformation. So within this vessel is made of stainless steel. So within this vessel, within this reactor, you can see some white solids here. This is a hydrate. So this is actually the methane hydrate. So, and so you can even ignite, then burn the hydrate here. So you can see that small white solid. It looks like ice, but there isn't a flame over this crystals. So this is because the methane is ejected from this dissociating hydrates, then make a flame over the crystal. This is a macroscopic view. Okay. So this, I would like to explain this crystallography relation between this crystallography to the macroscopic physical properties or thermodynamic properties. So this crystallography is closely related to the physical properties of the hydrate. So we can expect the large heat of hydrate formation for the hydrates. So this is very this is a thermodynamic properties, right? The heat of hydrate formation is quite large. This is ascribed to the water hydrogen bonds, and also water gas interaction also play significant roles for that heat of hydrate formation. Also, we can expect that a lot of gas molecules included in the hydrates. And so this properties is related to, again, the crystallography. So one gas molecule is trapped in one cage, and so we can have a lot of gas molecule within this crystalline compounds. So this high gas inclusion density properties relate to the other thermodynamic properties. So we can expect some large change of the system volume or large change in the system pressure through the hydrate formation dissociation. So if you form the hydrate, so a lot of the gas molecules are enclosed within this solid, and so the system size may be a shrink, and also the system pressure is decreased. But if you dissociate the hydrate, a lot of the gas molecule ejected from the, ejected from the hydrates, and then so large volume change, large pressure change, large pressure increase you can expect. And finally, so I would like to state different property. So this is a selective inclusion of gas. So depending on the chemical species of gas, how easy to form hydrate is different. So phase equilibrium condition is different. Some molecules easy to form hydrate, but other molecules difficult to form hydrate. This is depending on the crystallography of the hydrates. So there is some variation in the size of the water molecule cages, but so this geometry is there is some limitation. So there's not so big variation in the size of the water cage, and so specified size of the cages. So the cage size is correspond to the size of the gas molecule, the fitting into the inclusion of the gas molecule, and so we can expect some molecules easy to form the hydrate, but other molecules it is difficult to form hydrates. This property may be utilized for the gas separation. Okay, so again, the four physical properties here, and there is some notes here is a possible application of the properties. So high gas inclusion density property may be utilized to the storage of the energy or and the transportation. So natural gas or even hydrogen can be stored in the form of the hydrates. That is utilized for the energy storage transportation. And maybe other application is a molecular storage of some toxic, explosive, combustible molecules like ozone. If you have ozone, but ozone from the hydrate, ozone is maybe toxic and quite reactive, and it is dangerous. But if you form the hydrate with ozone, the ozone is wrapped into the water cage, and so we can establish the safe storage of such dangerous compounds. And then so large volume change, pressure change through hydrate formation dissociation, maybe we can expect some mechanical engineering applications, like even thermal engines to produce the power through the hydrate formation dissociation possible. Such maybe utilized to drive some actuators to control the mechanical system. And then, so selective inclusion of gas can be utilized to the separation purification of the aerosol mixtures, like even for the carbon capture technologies. So we can utilize the hydrate. And also desalination, so to produce pure water from the seawater is one of the representative application of the hydrate. And then large heat of hydrate formation dissociation property can be utilized for the thermal energy storage, particularly for the storing the cooler energy, or so we can establish a heat pump cycle or refrigeration cycle, repeating the formation of the hydrate dissociation. Okay, so these are some applications. Also, I would like to mention about these two unique applications. So one is firefighting. Hydrate can be the firefighting agent. So if you have a carbon dioxide hydrate, that is made up of the carbon dioxide and water. And so if you put the carbon dioxide hydrate into the fire, into the flame, so hydrate dissociates. And then, so hydrates dissociate. And so there is a CO2 and also the water. And the water, it may evaporate into the steam. So that lower the temperature of the firing system and then extinguish the flame. Or CO2 and water maybe work as to cut the supply of the oxygen to the flame. And that's we can utilize some hydrate as a fighting agent. Also, you can even eat the hydrate. This is a one unique application. So you can eat the CO2, carbon dioxide hydrate. So this is maybe the sparkling solid application of the hydrates. And then, so I want to move into the much more detailed research aspect of my talk. But so you may hit upon the hydrates engineering practice. So to representatively engineering practice may be the natural gas recovery or natural gas production from a naturally occurring methane hydrate. Even in India, I think that so Indian government have some interest to produce the natural gas. So because you have a lot of naturally occurring hydrates and even in the around the Indian Ocean. But I don't talk about this today. And also in the worldwide, so flow assurance in the oil and gas industry related to hydrate is a major research topic. So because the hydrate may block the oil and gas transmission lines, pipelines. But I don't talk about these two topics. Today, I would like to talk about much more some novel technologies towards the carbon neutral age. Okay, so first topic, I would like to talk about some chemical physics aspects on my recent study. So because this is this study to provide the answer about the hydrate thermodynamics, why the heat of dissociation hydrates is quite large, even sometimes larger than that of ice by 50% or greater. So, but there is no clear answer about this, at least before this paper. So we published in 5 years ago. So we may intuitively expect strong water-water hydrogen bond may be responsible to such a big dissociation heat of the hydrate, or maybe some contribution from the gas molecules that trapped in the cages. So to provide the much more theoretical or clear answer, so we performed MD simulation and analyze the data. So MD, again, this is just simply that movie from the molecular dynamics simulation. But if you do the molecular dynamics simulation, we can get all of the information from them in terms of a macroscopic kinetic motions. That is closely related. That is related to the macroscopic thermodynamics. This is a statistical mechanics. And so if we do the molecular dynamics simulation, we can understand all of the energy, microscopic energy, and then that is utilized to define the macroscopic enthalpy or internal energy of the system. And then so we did molecular dynamics simulation to reproduce the hydrate heat of dissociation, or including ice. So these are the experimental results. The heat of ice melting is 334. This is with the units of kilojoule per kilogram. This is well-known number. So, but you can see that the corresponding value of methane hydrate. Methane hydrate has the 434 kilojoule per kilogram of heat of dissociation. There is an like 30% difference between the ice and methane hydrate. So this is a mystery of the thermodynamics for this water system. So we reproduce that from the MD. So the absolute number cannot be reproduced because the molecular dynamics simulation is not really work with the true water. We have more or less the model of water in the computations, but so we reproduce the planes in the size of the heat of dissociation like this, and they analyze the data from the molecular dynamics simulation. And so we observe the hydrogen bond energy in the hydrate is actually smaller than that of ice, significantly. So probably this is the water-water distance is not, it's large in the hydrate. So because the hydrate has an cage-like structures, and thus, so hydrogen bond is weaker in hydrate compared to the ice. But we have gas-water interaction, actually, and in hydrate. That is responsible for the greater hydrodissociation heat. So gas-water interaction is quite significant. That is compensates the weaker hydrogen bond, water-water hydrogen bond energy. So this is a new recovery, I think. And that's, so gas-water interaction is quite important chemical physics to understand the hydrate's macroscopic properties. And then I would like to then talk about the one application. So this is a hydrate-based refrigeration. So I think that from my group, I have two publications. This is the number of publications limited, but 15 years ago, we published first paper and on the hydrate-based refrigeration. That was a joint project with the Tokyo Electric Power Company and the Japanese heavy industry, IHI. So you may feel bad with the name of Tokyo Electric Power Company because of the accident of the nuclear power station. But I had some contact with this electric power company. So, and then so recently I decided to revisit this novel technology. So after that, so particularly after the accident in Fukushima nuclear power plant, so Tokyo Electric Power Company, so they closed the company. They didn't any research work So so I once moved away from this topic, but recently I decided to revisit it's promising and novel technology. Okay, so do you know the current technology that is utilized for the air conditioning or residential refrigerator? That is in terms of thermodynamics, that is an inverse Rankine cycle, utilizing the vapor compression and the vapor evaporation. So usually the working media is hydrofluorocarbon. That is not necessarily very good for the environment. And also one problem, one negative aspect of such inverse Rankine cycle, the performance of the refrigeration system cannot have the further improvements. We cannot expect further improvements. This is very mature technology. And so we can not expect the improvements anymore about the inverse Rankine cycle refrigeration system. And then, so I would like to propose the hydrate cycle for the next generation of refrigeration system. So because we can expect maybe the higher COP can be obtained because that is related to big, large dissociation heat of hydrates. So if you have a one more of the hydrofluorocarbon, and that heat of evaporation or heat of vaporization of one more of the HFC is quite smaller than that of the hydrate that is formed with the one more of HFC. I think that generally heat of formation dissociation is 4 times or even 8 times greater than that of heat of evaporation, vaporization of the unit mass or unit mole of the working media. This is a thermodynamic background to expect the high efficiency of Hydrobased refrigeration system. And also, we may construct the environmental friendly refrigeration system because noble gases such as krypton can be utilized for the Hydrobased refrigeration system. So the krypton is, the amount of krypton is quite limited, but that exists in nature. And so that is no harmful to the environment. And so we may expect much more environmental friendly refrigeration system compared to the inverse Rankine cycle. And also, depending on the guest compounds, we may expect the low operational pressure for the hydrate. So that may be related to the safety aspects of the system. And so in the paper we published 15 years ago, we already stated the advantageous points of the hydrates refrigeration system. So because in the hydrates system, of course, we have water and we have the gas, that is a gas. And so the most, the greatest power required to drive the refrigeration is the compression of the gas. So the problem is that the compression of the gas. So you should know very well about the temperature increase through the adiabatic compression of the gas. So this is a problem of the compression because the temperature of the gas significantly increase if you have a compression. But if you have water here, so water absorbs the enthalpy increase in the temperature. And so temperature increase can be suppressed with the existence of water. And that's the compression process of the hydrate system. It's very close to the isothermal compression. That is, that should be idealistic in terms of the engineering thermodynamics. So because of this, nature. So we may expect the low input work. Low work is necessary for the compression. The compression efficiency is good in the hydrate refrigeration system. And that is related to the better total efficiency of the hydrates refrigeration system. In the hydrate refrigeration system, it's schematically illustrated here. So so you have gas and water, and then compressed with these compounds, and to increase the pressure, and then form the hydrate from the gas and water contact. And the heat of hydrate formation is released into the warmer environment. This is a high temperature reservoir in terms of engineering thermodynamics, thereby forming the hydrate. Then the form of the hydrate is pumped to the expansion valve to depressurize the hydrate, and then dissociate the hydrate at the lower pressure, low temperature side. Then, so the hydrate absorbs the heat of dissociation of hydrate, and thus the space may be refrigerated. So, repeating the forming hydrate, decomposing the hydrate, so you can establish the hydrate cycle to realize the heat pump from the low temperature side to the higher temperature side. Okay, so recently we revisit this system, and then so what we have done recently is a formulation of this hydrate-based refrigeration system. So here, state one on the pressure temperature diagram. So state one, there is no hydrate. There is only a water and a gas, and the water and the gas is compressed to the higher pressure. And then, so during the compression system, the gas temperature should increase, but water temperature should not significantly increase. And that's after the compression, the mixed temperature is not very high. And this system would be cooled by the high temperature reservoir. That is maybe the atmosphere, or maybe river water. Even the seawater can be utilized as a high temperature reservoir. And then form the hydrate. The form of the hydrate is depressurized down to the lower pressure side. And then here, so the hydrate is dissociated, and the heat of dissociation is utilized to cool the lower temperature reservoir. This is a hydrate cycle illustrated on the pressure and temperature diagram. Then, so we obtained two conclusion. One conclusion is, of course, dissociation heat of hydrate is quite important. It's dominant factor for the better COP, but also the compression work of the gas quite significant. This is mostly evident, but so because such adiabatic compression is important, it's a dominant process in terms of the input energy, input power, and so polyatomic gas may be better to obtain the better COP. So this is some, I do not go into the details about that. So this is some example of the formulation of that, our theoretical analysis. This is a COP defined as a utilized cool energy. And also that is divided by the power input to drive the thermodynamic cycle. That is the compression power. That is mostly compression power for the gas. This is the enthalpy change from state 1 to 2 of the gas. So there should be the other contribution, but that is not significant. Also, if we go into some details about this compression power, so we can see that effect of the kappa. This is a capacity ratio. So that indicates the polyatomic gas is better than the monatomic gas. Okay. And then, okay, I have some more 5 minutes or something that's, I would like to talk about the carbon capture technology utilizing the hydrate also. So we published recently that at least 2 papers, a couple of papers on this topic. Carbon capture from the hydrogen carbon dioxide gas mixture using the hydrate formation. Okay, so this is some cartoon indicating the integrated coal gasification combined cycle. In the age of carbon neutral, this background may not be very appropriate. But so if you have coal, so coal may be utilized to produce a fuel gas through the catalytic reaction. So, but this is not necessarily coal. If you have any fuel, like even biomass can be utilized as a first source of the fuel. So even biomass can be gasified into the hydrogen and finally carbon dioxide. And so in this generation of the hydrogen process, we need pre-combustion capture with CO2 before providing the hydrogen into the combustion turbine. And the combustion turbine may be also linked to the steam turbine to do the combined cycle power generation. So in this next generation hydrogen-based power generation, we need the pre-combustion capture of carbon dioxide. So I think you know very well about carbon capture. So chemical absorption and membrane or physical absorption is known as a already established technology, but chemical absorption that depends on the use of the amine compounds that is toxic and corrosive to the metals. And there's a lot of people in the industry want to avoid the use of the amine. Also, physical separation, there should be some drawbacks because of the membrane, the representative technology. Membrane is readily blocked, and that's we need frequent maintenance of the membrane. Or before that, so membrane itself is very costly. The price of the membrane is very, very high, and so we should consider different technologies, different from the chemical, physical. That is maybe the hydrate-based gas separation. So in principle, hydrate-based technology only utilizes the water. And so this technology may be the very environment friendly. Okay, so if you have a mixed gas, so one component of the mixed gas is easy to form hydrate. And so if you form the hydrate from the gas mixture, one component can be concentrated into the Hydrobased. And so if you form the hydrate from the mixed gas, so you transport the hydrate to the decomposing reactor and then decompose the hydrate. You can get the purified gas. This is a concept of the Hydrobased gas separation. Okay, so this is our experimental data showing that gas phase compression and change. So this data indicates the compression concentration of the hydrogen in the gas phase, and the lower side data indicates the concentration of the carbon dioxide in the gas phase. So you can see the increase in the hydrogen in the gas phase and the decrease in the CO2 in the gas phase through the hydrate formation. And this graph shows the hydrate side composition. So you can see the higher concentration of CO2 in the hydrate and the lower concentration of hydrogen in the hydrates. So particularly, so in this study, we observed the structure one hydrate. Structure one hydrate is a pure hydrate formed with water and hydrogen and carbon dioxide gas mixture. Shows in terms of the gas separation performance, structure one hydrate may be good, but structure one hydrate may have the drawbacks because of its high equilibrium pressure. We need a high pressure to continue the hydrate formation. Okay, so I should summarize my presentation, or may I talk?
You can go for another 5 minutes, Professor Ohmura.
Thank you very much.
Yeah.
Okay, so you can see that some phase equilibrium condition. This is for the structure one hydrate. So if we have some additional helping gas, so for example, ammonium bromide may be very good to lower the equilibrium pressure of the hydrate formation. But in this case, the separation performance was not very good with the help of the TBAB. So hydrogen concentration was also very high. Also, the hydrate phase, there is some hydrogen. But with structure one hydrates, there is no hydrogen in the hydrate phase. And also, 100% carbon dioxide was detected from the carbon dioxide for the hydrate without the use of the help of ammonium bromide. And so we should find some compromise because the structure one hydrate has a good performance in the gas separation, but the drawback may be the high pressure. And then the low pressure may be advantageous for if we utilize TBAB, but separation performance is not very good. And thus we tested structure to hydrate. So phase equilibrium condition is between the structure one and the ionic TBAB hydrate system. So, and this is a result, the continuous separation with tetrahydroplan to form structure to hydrates. So this trial was quite successful. So we observed the increase in the hydrogen concentration up to the 90% in the gas phase. And in the hydrate phase, there is no hydrogen was included. Only 100% of CO2 was detected in the form of the hydrates. And thus I would like to conclude structure to hydrate may be a good compromise. So between the structure one pure hydrate and the hydrate formed with ionic system. Okay. So we did some physical chemistry characterization and published again the paper, general paper. Okay, so this is the final slide for my talk. So I would like to summarize. The hydrate heat pump may be as only one candidate for as the next generation efficient refrigeration to follow the existing inverse Rankine cycle system. And also Hydrobased, the gas separation may be superior to the mature technology, chemical absorption, or physical separation technologies, while keeping the cost is the same. And for other technology today, I could not talk about maybe the hydrate may be utilized phase change materials for battery cooling. This is maybe utilized for the electric vehicles. And also the hydrate-based engine may also be the attracting application. So this is a reverse cycle of the hydrate heat pump. So, and finally, I would like to emphasize the understanding of the fundamental physical chemistry is always very important as a foundation of the application, the Hydrobased technologies. Okay, I would like to finalize my presentation. Thank you very much.
Thank you, sir. So we have some questions in the chat box we'd like you to answer. So Mansi Lavekar has asked, compared to the crude oil extraction, how economical is the process of methane extraction from the hydrates?
Extraction of the so can I confirm the question again?
Okay. So Mansi Lavekar has asked, compared to the crude oil extraction, how economical is the process of methane extraction from the hydrates?
Methane extraction.
Methane extraction, yes, sir.
Methane extraction from the naturally occurring methane hydrate.
Yes.
So I'm sorry, I'm not very familiar with the economics about that methane hydrates exploitations, but I think that roughly speaking, that I think that the price, it depends on the price of the crude oil. I think current situation of the crude oil price and in the worldwide market, that I think the hydrate has no cost merit. And that's so if, like say, so the price of the crude oil increases, I think maybe by 3 times. So we may consider the exploitation from the natural methane hydrate. But so I think, but for the methane hydrate resource, we may expect a different aspect. I think it's energy security. So because even the oil and the natural gas, the fuel is very limited to the limited area, like Middle East. But if you have a methane hydrate in India, you can get the methane from your territory. That can be the energy security. This is true for the Japan. We import a lot of fossil fuel from Middle East, like Australia or Alaska. So we don't have the resource in our country. And so the price of the methane produced from the methane hydrate may be relatively high. But so it may be important to have your own resource within your territory.
Okay, sir. That was a great answer, sir. So Mansi has again asked, how is the gas transported from the seabed extraction units?
Seabed,
Yes, sir.
the gas transportation from the seabed to the upper side.
Yes, sir.
Okay, so I think again, this is some natural gas production question, and so that's I'm not very familiar with that, but I know some. I think that one economical way is a dissociating hydrate, utilizing the methane hydrate, maybe dissociating in the pipeline from the surface of at the bottom of the well. So if the hydrate dissociate, so then bubbling, that is a buoyant force. The gas is self pumped up from the bottom to the upper side, I think. This is a kind of gas lift mechanism. Dissociate the hydrate within the well. So hydrates automatically float up. This could be an efficient way, I think.
Okay.
Otherwise, you need some pump. That should require very additional input of the power. That can be the problem.
Saswat, I have typed some of the question which was there in YouTube in the chat box. You can ask from the chat box directly.
Okay. So the next question is, what is your take on hydrate-based energy storage?
What is
your take on the hydrate-based energy storage?
Can I confirm that?
Yeah, hydrate-based storage of methane or natural gas. What do you think, whether this is a good technology or whether it will be a mature technology compared to other mature processes?
Okay. Yes, I think that natural gas transportation in the form of the hydrate, I think that may be economical, depending on the situation. So we did a lot of work 10 years ago in Japan. So I worked with Mitsui Engineering Shipbuilding Company. So they were really the leading industry sector. And generally, in the situation in Japan, import the natural gas from Middle East, for example, in the form of LNG. So we do this currently. But if we replace this liquefied natural gas, replace with the natural gas hydrate, we may expect 20% cut of the transportation cost. That was some cost estimation, 20%. So 20% is not very big. So if the industry starts something new technology, so 20% cost cut, so they don't believe. 20% cost cut may be very small. So I think so. We should like 40% cut or 50% cut. So I think the society will move, but 20%. So I think that the technology is not commercialized even in Japan. But so again, I would like to state other aspects about the transportation of natural gas in the form of the hydrate. So we have water together with the natural gas. And that's if in the situation, so the water is very important. Like, and the island countries, they want to the pure water. So in that case, I think the natural gas hydrate transportation quite efficient. So water is also significant. This may be also true for the use in the military. So in the front of the wall, so if you need the natural gas together with water, so natural gas hydrate may be good to provide energy as well as the water. And also related to the water. So one good aspect of the hydrate is the safety. So if you have some accident with LNG, if once that is ignited, so there should be a significant explosion. So we cannot do anything once LNG is ignited. So we should just go away from the accident. But hydrate, it is quite difficult to keep the flame over the hydrate because hydrate dissociate. If you dissociate the hydrate, there is a water. The water or ice form. And so water or ice, they prevent the flame over the hydrate. And thus hydrate is much more safe. So we did this the combustion science study previously. We reported in the energy and fuels. So we measured the propagation of the speed of the flame over the hydrate. That is compared with the conventional gases methane case. So there is a significant difference, like 1,000 times the propagation of flame over the hydrate is slow. That is quantitatively indicate the safety of the natural gas hydrate as an energy transportation medium.
Thank you, sir. So the next question we have is, can ozone be used for water treatment?
Ozone, yes. Ozone is practically the strongest oxidant, strongest compound to oxidize in the world. Maybe theoretically fluorine, if you have F2, but F2 is too dangerous to use. But next to the F2, the O3, ozone is the strongest. And so ozone can be utilized for any treatment. And so water can be, water treatment may be the representative application of ozone. For example, in Japan, we have this. So like 30, 40 years of history, utilizing ozone to purify the water, to provide the water to the tap. But the problem is ozone. So we cannot store ozone. And so we always need electricity to produce ozone. And so utilization of ozone is not so widespread. And thus, so I would like to propose the ozone hydrate to store and then transport ozone easily, even if you don't have the electricity. If you have the ozone hydrate, so you can utilize ozone anywhere.
Yes, sir. Thank you. And we have one more question. Yes. What is the most sustainable way of energy production?
Sustainable way. I think it. So we should. I don't know. I don't have the clear answer, but I think that worldwide the society should move to the so-called renewable energy, and solar energy, and maybe wind power generation should be the major source of the energy. I think it is quite sustainable. But the problem of such a natural energy, so there is a strong fluctuation. So solar energy can be utilized only in the day of the sun, the sunny day. And the wind power generation also, we need to expect the strong wind. And so there is a strong fluctuation for the such a natural sustainable energy. And thus we need to store the energy in some form. So one is that battery, but battery is not very efficient. There is a significant loss, the charging and discharging, and also the application of the energy. It's the use of the thermal energy quite often, like refrigeration or air conditioning. In that case, I think, so if you have the strong sunshine, so you have a lot of solar energy, power generation, you should form hydrate and then store the hydrate. And then you may use the hydrate dissociate to cool for the air conditioning for the cloudy day. That may be the use of the hydrate in the sustainable energy age I would like to propose.
Yes, sir. We would like to end the show right now. So I'd just like to say that we are very thankful for you sharing the valuable insights on the properties of the clathrate hydrides and its application for various processes. We will also appreciate your great contribution to achieving a carbon neutral society. I would also like to thank Professor Rajneesh for joining us today. Your presence has been great, has contributed a great deal for smooth conduction of Dr. Ohmura's talk. So folks, that was a great and exemplary talk marking the end of plenary lecture series. Stay tuned for next year's ChemPlus for more such exciting events. Thank you, sir.
Thank you, Professor Ohmura. It was really nice listening to you, and look forward to meet you physically very soon.
Yes.
Have a nice evening. Have a nice evening.
Thank you very much. Thank you. This was very exciting to me, and I feel very happy to receive quite a lot of questions about energy issues.
Thank you, Professor Ohmura.
Yeah, thank you very much.